Welcome. Last session we spoke about Deque. What is Deque and what are the operations can be done using Deque? And also we spoke about the time complexity of each operation. For example, insertion at friend, deletion at friend, insertion at rare, deletion at rare, and accessing element. All these operations we discussed actually. So in this session, I will try to implement Deque using a double linked list. Right? Okay, let's start. So for IO operations, I will include, by the way, I am trying to implement using C++ here. Okay, namespace, std. So let us create a linked list here, node, up class, node, public, shit, integer data, node star of next, node star of previous. Create a node constructor, it will take integer d. Okay. I will try to initialize data next with null, prior EV also null, right? That's it. Okay, now we are ready with the linked list now. Up node. Okay, this is the node for the linked list which contains data next and previous nodes. And also we implemented constructor for that to initialize the data. Now let us create a new class called Deque. Okay, which has a private. Here we'll create node for front, node for rear, right? Now we'll create a constructor for that. Deque will try to initialize these two things. Front equal to null by default, and rear also equal to null. We can do here also. Right? Actually, we can use front of null. Now rear of also null. Okay. 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 This is what we can create a constructor, and also we'll try to finish is empty. We'll try to return front equal to null. This is the case, then this is empty. Okay. As we discussed in linked list, all the time complexities will be of one only. Let us try to implement now insert at front and its time complexity of one. Let us see how it can be done. Void insert a front of integer data. Okay, so what we can do is new node equal to new node of data. So we just created a node here. Let's check if E is empty. If it is empty, then front equal to new node, and rear also both are new nodes. Okay, otherwise we need to do this one. Actually, what we need to do, front equal to new node next, next equal to front equal to. So basically what we are doing, if you see that there are no loops, nothing, that's why you can say this O of 1 gram complexity. In this case, what we are doing is front previous is equal to new node. Okay, front previous, and new node next equal to front node, and front node equal to new node. So this thing actually will change, will insert at the front. Okay, basically front becoming new node. Okay, okay. Now let us insert from the rear. Okay, insert at rear. It's a time complexity of 1, just opposite of whatever we have we have inserted in the front actually. Okay, now what we can do is insert at this time complexity is of 1 time complexity. Okay, now just create a new node equal to new node of data. Okay, now check is empty. If it is empty, then front equal to new node, rear also new node. Okay, done. Else what we need to do is we need to see rear next equal to new node, and new node previous is equal to rear equal to new node. That's it. Okay, now let us insert or delete from front. Delete this also will take of 1 time complexity. If you observe here in insert rear, there is no loops, nothing. Simply we are trying to insert at the rear position. Okay, now we'll try to delete from the front, right? delete front if is empty out is empty and nothing to delete here, right? Else check if front equal to null, rear equal to null. We need to make this as empty now. Else what we need to do is temp equal to front. Okay, sorry, front equal to front next. So basically we want to get the front node, right? Front node only we need to delete. So this is the temp is the front node. So in case like front next is null, that means only one element is there. Then just do this and return from here. Front preview is previous equal to null because we want to just delete a temp. This also will take open time. Like if you observe that nothing is there here. No loops, nothing here. Okay. Similarly, let's delete from the rear. Delete element from the rear. This also will take one time complexity. Okay. Let us implement this. Delete rear. So basically we will check is empty. Then we need to see out. Sorry, Deque is empty. Is empty. Nothing to do here. Return. Otherwise, what we need to do, we need to get the element from the rear. Okay. Now rear equal to rear previous. Okay. Rear equal to null. Then front equal also null. Okay. Else rear next equal to null. Delete. Okay. We're trying to delete from the rear side. Okay. Now other operation is like a get from the front element. Get the front element. This also will take one time complexity. Okay. So int front. Okay. If it is empty, nothing to do. -1 will return here. Deque is empty. Okay, return -1. Otherwise, it's very simple actually. Okay, just return front data. Okay, this also, as we discussed, this is just one time complexity. Rare also, as we saw, similar to this get element from rare with one time complexity. Okay, so similarly here, if E is empty, what we need to do? Cout Deque is empty. Return -1. Otherwise, just return rare data. Perfect. So what we will do is we'll try to display it just for our understanding purpose. What we will do is if is empty, okay, cout is empty. Okay, return. Nothing to do here. Otherwise, we need to start from front. Okay, iterate temp is not equal to null. Cout temp equal to next. Okay, after ending this inline. Okay, this is the all operations we covered here, like insert front, insert rear, delete front, delete rear, reading front element, reading rear element, and also we are displaying. Let us now start verifying this through main. From the main function, what we will do is we'll try to create deque. Okay, deque dot insert front one, deque dot insert front two, deque dot insert rear 3, deque dot insert rear 4. Okay, now let us display these things. Okay, and see what happens. G++ main.cpp. So you observe that 2 is inserted, 1 inserted, after that 2 is pushed next front element. That's why 2 is the front element now. And in the rear we printed 3. So here actually in this case this will be one front, rear also same thing. Here when by the time it comes, it will come like this. The DQ looks like this. From here to 1 3, by the time we push insert the rear once again like this. That's why we are able to see 2 1 3 4. Okay. Now let us delete operations. Let us do that. Deque dot delete front. Okay. Delete front means it should print. Basically here it prints as I mentioned here. And by this time actually it should deleted front. Now it should be. Let us check that. Deque dot display. Right, 134 after deleting prompt. Now let us delete from the rear. That means it should print 1 and 3 only. Let us see that also. Right, right, 1 and 3. Now what we can do is we will try to see out deque dot front see out deque dot rear. Let us see what it should print actually 1 and 3, right? Correct, 1 and 3. Now let us delete once again deque dot delete front deque dot delete rear. So this time actually all elements got deleted. Now if I do deque dot display, it should print queue is empty. Right? Let us see that. Perfect. So that's about C++ implementation for deque. And also we discussed all the operations and its time complexity as part of this session. Thank you.